All right, so today we're going to be talking about the call stack and recursion. I think we might have seen recursion in week one with one of our challenges that were solved. But yeah, I just want to give a more formal idea of what recursion is in case you've not seen it. Talk about why you might want to use recursion, what it achieves for us, and yeah, all the details there. So for the remainder of this week, or I guess for this week, we're going to be focusing on data structures and algorithms. That's the focal point here. So recursion, the way I want to kind of just lay it out is that it's not always useful, but it's just something that should be in your toolkit, right? So if you're solving a problem, recursion might be a better approach to certain types of problems. Not always, but it's just something to be something that you should have at your disposal if you need to solve a problem. So let's talk about the call stack first, and then we'll get into recursion. So first is the call stack. What is a stack in the real world? So I'm going to ask an audience member to answer this. If I asked you what is a stack, just we use stacks sometimes in our normal normal daily lives. If I were to ask you what is a stack, just in your own words, can someone describe that to me?
Stuff on top of other stuff.
Simple enough, yeah. So again, we deal with stacks. Like again, when I think of a stack, I think of maybe a vertical pile of objects. Yep, stuff kind of on top of each other. So one example is a stack of plates, right? So this is what I visualize when I'm thinking about a stack. We have a stack of plates here where we put one at the bottom, then we put one on top of that, and one on top of that, and so forth. And then the way we interact with this stack of plates is that if we want to grab a plate, I would assume that most of us would just grab the one on the top, right? You don't try to like slice the middle and do like a tablecloth trick. Usually, let's just say we're going to grab from the top here. So we grab items from the top, and then when we're putting them back on, we put them on the top also. So that's how a stack of plates works, right? I assume, hopefully, we all kind of understand the principles of stacking plates. So that is, in the real world, we deal with a stack of plates. But then, what is a stack in the programming world? Luckily, it's similar concepts. Now, again, in the programming world, we don't necessarily have physical things that we're looking at, but the concepts are the same. So it's a data structure that stores objects in an ordered manner. So we talked about the idea of ordering, like when we worked with lists. Lists are ordered containers. When you insert, when you add items into a list, they're going to stay in that particular order. They're not going to like randomly shift or like be sorted automatically. They're going to maintain their ordering based on how they're inserted into the container. A stack is also an ordered container. Provides a single insertion point and a retrieval point. So the terminology here is the push and pop actions. So when you push something onto a stack, you're adding a new plate on top. When you pop something, you're going to pop it from the top. Generally, the way stacks are implemented, you do not get to take a plate from anywhere in the stack. You always take from the very top. So that's what pop is referring to, where you always take the top plate no matter which one it is. All right, the buzzword here is LIFO, or I guess acronym here. LIFO means last in, first out. So again, the last plate that you put onto the top of the stack of plates is the first plate that anyone's going to grab off of it, right? So that's what LIFO is, last in, first out ordering, or I guess retrieval. Any questions on the idea of this data structure? Kind of how you access items, how you add items. Again, just think of that stack of plates. Again, I'm a visual person, so hopefully that might work for you. But when you're adding items into this data structure, you always add on top. You push onto the top of that stack. And then when you want to take something off of that, so if I want to grab a plate, I grab from the very top and I pop out a plate. So that plate is no longer part of that stack. I have that plate in my hand and I can do whatever I want with that plate. In this case, for the programming world, I have some data that I took off my stack. So that data is no longer in the stack. I have it in my hand and I have it in my application. I can do whatever I want with that piece of data. Questions about stacks, the stack data structure? All right. Oops, I was going to hide that. But yeah, what's an example of a stack that we use in daily life? I kind of show the answer there, but someone want to just tell me where you see stacks used in the programming world. I bet all of us use it every single day.
The lists.
list. Could you elaborate on that, Justice?
Sure. So every time we've put something on, we've just appended and or pushed and then pop off of the list. I know we can take stuff off, but I think that's like technically a lot more complicated because it has to move all of the other things.
Yeah, so that's a good distinction. So again, there are many data structures that we may encounter. The two most popular ones that we've been using have been lists and dictionaries. But lists and stacks do have differences. So we could implement a stack using a list, but let's talk about the differences. Again, this is kind of getting into our data structures discussion, which will be later this week. But yes, a list and a stack do allow you to add items to the end, but a list actually lets you insert items into the middle if you wanted to. A stack would not allow that. So a proper stack data structure would not let you insert something into the middle, won't let you access anything to the middle. The only retrieval point is at the very top. So you can only add to the top and get from the top. You can't really search through a stack like a traditional stack data structure. But I guess one example that we see every day that maybe we don't really realize it's a stack is our web browser history. So let's think about how our history works in a web page, right? So I'm actually going to go to my browser if I can find it. There's my browser. Let's go to a few web pages, right? So one thing, let's say I want to check the news. I'll go to CNN.com. There should be some news here. All right, we got some politics going on, yada, yada, don't really care. Let's say now I want to go to ESPN.com, right? The Super Bowl was yesterday. I was rooting for the Bengals. Unfortunately, they lost. But let's check out what ESPN has on their front page if they'll load. All right, so I have a Super Bowl summary. Yeah, again, it's a close game, so it's competitive. All right, so I went to CNN.com and then ESPN.com. Let's go to one more site. I don't know what else is out there. There's a bunch of sites. Let's just go to Coca-Cola. No, that's not one. Let's just go to QuarterByte. All right, so I'm going to go to QuarterByte. We use this for our application process. So I went to CNN.com first, then to ESPN.com, and now I'm on QuarterByte, right? If you think about your history, it's stored as a stack. So if I actually drop this down, notice that the most recent item. Sorry, let me add one more here. Just get one more item in my history. I also want to name a cool site that I could check out. That I could display here. Edgar, your audio has some issues. I can't quite make out what you're saying, but I'll just pick a site. I'm struggling to think of something. Let's just go with hotwire.com. That's a site. All right, so now I went to Hotwire after going to QuarterByte. So if I look at my history right here, notice my most recent one is at the top. Then after that, and then CNN was the first one, but that's at the very bottom of my stack. All right, so actually, if I hit the back button, it's going to go to my most recent item. So it's actually this data of what's stored in the web browser history is stored as a stack, so that if I hit the back button, it's going to pull the first item off that stack. And that first item that's accessible is QuarterByte, because that was the most recent item added to my stack, right? It's last in, first out. So the last item that was added to the history was QuarterByte, so it's the first item that I get back when I hit the back button. If I hit back again, now my stack only has 2 items in it. My history has 2 items. It has CNN and ESPN. So if I go back one more time, it should go to ESPN because that was the most recent one before QuarterByte. So I hit the back button and notice I'm taking to ESPN. Right, and if I head back one more time, this is the last item in our stack. So CNN was at the very bottom of our stack. We pulled everything off the top. Now we only have CNN. Yes, I have an ad blocker. We have CNN left, and that's the bottom of our stack. If I head back one more time, it'll just be, again, my default page. All right, so again, we use stacks, in technology often, even if you guys don't realize it. So that's one great example of a stack data structure that's used. Any questions on stacks here? Okay, let's continue. So now that we talked about what a stack is, let's talk about what the call stack is. So a call stack is a programming term. It's an ordered collection of execution contexts. Now this is kind of a very technical bunch of words here, but just understand it's storing some stuff in a stack data structure, is if you want to kind of simplify it there. We have an execution. This is also known as our execution stack. So basically, each line of code that our application is going through, it's going to add it to the call stack one at a time and execute it. Once a line of code is completed, it gets pulled off the stack. So we have this execution stack. We may put a bunch of stuff on it, and once it completes its execution, it gets pulled off that stack. A lot of times we're just doing one thing and we're done, like printing out to the console. We add that print statement to the execution stack. It completes, it does its job by printing something out to the screen, and then it's done with its operation, so it's pulled off the call stack there. Function calls only complete once their entire logic or body of logic is completed. So if we have a function that has 3 lines of code in it, all 3 lines of code must execute in order for that function to complete its execution. So this is how we can build up the call stack when we call functions within functions within functions. All right, any questions about that? Hopefully that's pretty straightforward, but I want to make sure everyone kind of understands the idea of a call stack. So this is what your application uses to keep track of what it needs to execute. It piles the stack up, execute things, and then take stuff off the execution stack or the call stack. All right, I think we're good with that then. Let's go to, sorry, I need to pull over a tab here. Toss this over here. Okay, so we want to talk about, I guess I have that tab open. Let's take a look at this example. So on the curriculum page, we have some examples. I'm going to copy that code just to save some time. Let's put this into a new file. Let's call it call stack.py. I'm going to paste that code that I copied from our curriculum page that has some pretty simple function going on here, but we just want to see what this does for our call stack. So here, I have 3 functions, not really uniquely linked or cleverly named. I have first, second, and third as my 3 functions. I start off my execution by calling first. This is the first thing I do, right? So remember, functions, they don't automatically execute what's in their body. They only execute when you call them. Again, it's much like you have a friend that's going to do some work for you. You actually need to call them up on the phone and say, hey, can you do this work for me, before they will do anything. So here we call our function first, and then it's going to execute these lines of code. It's going to do a print statement. Notice we are calling a second function here, aptly named second. So we're calling into another function. So this line of code actually executes these 4 lines right here. Because we're calling it to that function. This line right here will not execute until this line fully completes. So I'm going to run all this stuff in my second function, which does a print statement. Then it's going to call another function. So we're calling a function within another function, which is totally valid. Nothing's stopping us from doing that. So third, going to do a print statement. Notice we're going to print out hello world eventually, and then do another print statement and return. So return is the end of a function. Anytime you see a return statement in a function, that means, all right, this function is completing its job, and that's going to be pulled off the call stack after that. All right, so let's actually take a look at this and see what the output is. Don't want to modify my code. Let's run Python call stack.py. Let's take a look at the output here. So if I can get my code and my output visible, that'd be best. All right, so I have my code above and my output below. So notice the order everything got added here. I have push, first function executing, and then after I have another push statement, second function executing. How did that happen? Well, when we get into our first function, we do the very first thing at the top, which is that push first function executing, and then we call into second. So second is going to print this line and then call into third. What is third going to do? Third is going to print another statement. So we get push third function is executing. Notice that the first and second function have not completed their execution. They're kind of waiting for third to complete its job. So third is going to do what it wants to do or what it needs to do. So here we print out push third is executing. We print out hello world, which gets printed out right here. And then we print out a pop, meaning I'm trying to simulate that we're done with this function. We're popping the third function off the call stack. So here, it's a pop action off the call stack and we return. So now the third function is resolving. And after the third function completes, we get to this line of code, which means the second function now complete because there's nothing more the second function really wants to do aside from this print statement. So the second function resolves. We return from the second function, which means second function is done. That means we can come back here, continue on with the first function, which is, first function resolving, and return right here. So you kind of see how that builds up and then builds back down. So that's that stack gets bigger and eventually builds back down. If we actually wanted to see this, VS Code should allow us to see our call stacks. Let me try this out. Hopefully I remember how to do this. So if I put a breakpoint on this hello world, so I'm in my third function. Let me try to run this through the debugger and let's see what VS Code actually shows for us. So I don't need my, I'll need this somehow. I'm going to go to the run menu, start debugging. I'm going to select Python, the current file. All right, so it's going to run and it's going to hit this breakpoint that I set up right here. So notice I'm halted in my execution right here. Take a look at what's on the left side here. There's actually a call stack panel that shows you what functions you've actually called before. So notice at the very bottom, there's something called module. We won't worry too much about that. That's just our file that's running. So that's a very base item of our call stack. But then on top of the module, we have first, because that's the first thing that we called, right? So that's added to the call stack. Within first, we call second. So again, first does not get removed from the call stack. It's still kind of executing, waiting to complete all of its actions. But we call second, so second gets added to the call stack here. And then second also calls another function, which is called third. So third gets added to the very top of the call stack. That is the current execution point or the execution context. All right, so we have a breakpoint right here. We're halted in our third function, but let's actually continue line by line. So I'm gonna go do the step over action. So if I go step, we're still in our third function. So third is still in our call stack. I'm gonna go one more time. When we hit this return statement, third should no longer be on our call stack. So notice third got booted out because third completed fully. We have only second and first on our call stack. We're going to continue, hit our return statement for second, right? That's our current line of code. Continue on. Notice that second is done. So that's off our call stack. And then we're left with first. That returns, and then we're done with our application. All right, so again, can be useful to debug, especially when you get like multiple levels deep down into a function. I want to know how you got into this point, right? In this case, it's not the best example, I'll admit, because there's only one way to get into third here. But what if we had like another function called fourth, that also happened to call into third? Fourth, if I could get this typed, let's say, this is a print statement of blah, we call third, and then prints, yeah. All right, so there's two ways we can get into third. What if I don't, what if my application has a bug in it and I don't know what's causing that bug? Well, maybe I want to set a breakpoint in my third, and then maybe I realize that the bug only exists when fourth calls it, but not if second calls it. So that'll kind of narrow down my search saying, okay, this only breaks when fourth is calling it. Is there something I'm doing here that is somehow breaking the logic here, right? So again, the call stack can give you identification of how you got to that point in code. Obviously, I'm not calling fourth here, but I could call fourth. That work. Does that make sense? You guys with me here? What the call stack is kind of representing for our application? Okay, so I kind of took the effort to kind of detail this in our example here. So I'm just going to go line by line, kind of what we just saw. Maybe this can be redundant, but again, we have our code here. So this is my code file. There's something called the global execution context. Just to simplify it, because I will admit I don't know the full details of global execution context. But if you think about it, like if you had a global variable for your application, that's what your global execution context kind of has in it. So when you start your application, everything that is kind of at the base level is your global execution context. Now, as we continue, if we execute our application, this red line represents where we are. So we just did this in our VS Code. It's probably better to see it there. We just do this kind of manually in our slides. When we're on this line, that first function gets added to our call stack. So again, it gets added on top of the global execution context. And then we continue on. The print statement actually gets added to our call stack also. This is a function we're calling, right? Print is actually a function. It's not just like something. It's actually a function where we pass it a parameter, in this case, a string. So that gets added to the call stack, but then that executes and completes. So that that print statement got added to our call stack and then removed because it completed its job kind of immediately. All right, so that's our output right now. Then we go to second. That gets added, as we saw. Now we're actually in our second function, right? We made a function call from within our first function. We add the call here. Gets added to our call stack. Continue on. Sorry, that went a little quick, but the print statement here, we're on this line. That print statement gets added to the call stack temporarily. That executes and completes so that we see the output, and that print statement's gone from the call stack. We continue on. I think we've seen this before. So prints, the third gets printed there, then the hello world gets added to our call stack, that completes. Continue on. All right, so when we hit the return statement, right here, this return statement, that's completing our second function call. So second should now be removed from the call stack, which we saw in our VS Code. We continue on, print statement from the first function gets added, that completes. So our output's kind of getting added there. Return statement here should remove first from our call stack. That should return, sorry. Yeah, so that's removed. And then after everything is run, our application is finished, right? So our global execution context will automatically be removed from our call stack, meaning we're done with our application. All right, what questions do you guys have with the call stack? Is this making sense? Do you guys understand the idea of function calls within function calls? You guys kind of see, my first function can call my second function, and that's totally fine. Right, I'll take your silence as everything's making sense. Great. Then let's go to the topic of recursion. So if we understand the call stack, we want to kind of understand that to understand kind of what recursion is doing here. So what is recursion? Recursion, I've defined it, recursion is something that employs recursion. Well, that's probably not a very useful definition, right? It's kind of referring to itself, like we're using the word within its definition. That's usually not the best definition we get. But a more clear example or definition is, what is recursion? It's something that references itself as part of its definition. I just want to show you guys a kind of like a silly Google trick. I don't know if you guys are familiar with this, but if you actually search for recursion, has anyone done this before? Search for recursion, and you know how Google kind of corrects you and say, well, maybe you made a typo. Okay, maybe I made a typo here. That's my bad. Let me click on recursion. All right, it takes me to a new page, but notice it keeps telling me, did you actually mean recursion? So you can actually just keep clicking that. And that's kind of like a Easter egg in Google. Again, it's a kind of like programming humor, but this is just an example of recursion where I can keep clicking this. It's going to keep calling itself over and over again. All right, so a little Google Easter egg there for you. But that is the idea of recursion, where you kind of define something by itself. All right, so what is recursion in the programming world? So it's a process involving breaking a bigger problem down into smaller versions of itself. A recursive function is something that calls itself. So in our former example, we had function first calling into function second. That's just a normal function call. A recursive function call would be if our first function called itself within itself. So if I had first and then within first, I called first again, that's an example of recursion. I think one example where we've seen recursion was the Fibonacci algorithm. So actually take a look at multiple solutions to kind of see that there are many ways to solve one problem. Sometimes recursion can be beneficial, not always, but let's actually take a look at the Fibonacci algorithm that we dealt with in week 1 and look at an iterative solution. That's where we use loops. And let's look at a recursive solution where we use recursion. So what are the main parts of recursion? There are two things that you need in a recursive design. You need a base case and a recursive case. So the recursive case is where you actually make that successive function call into itself. But the base case is like your ending point. It's a special condition or conditions, you've got multiple base cases, where the function returns without any more recursive function calls. Note here, if you do not have a proper base case, you can get into something called a stack overflow, where you keep calling into your function over and over and over and over and over again. And that's eventually going to cause problems because you're going to run out of space for the application and it'll most likely crash or give you some error message. So sorry, we're going to talk about the Fibonacci algorithm in a second, but let's talk about two different approaches here. We have recursion, which we're kind of talking about today. We have iteration, which is what we've been kind of doing before, right? Where we write while loops or for loops to kind of do something repetitively. So iteration is a process of doing something in repetition. This is where we use for loops or while loops. One note here is that all iterative solutions can be converted into recursive solutions, and vice versa. All recursive solutions can be converted into iterative solutions. So again, you're not forced to use one or the other, but there are reasons why you may want to use iteration over recursion, or you may want to use recursion over iteration. They're doing the same thing, right? They're both repeating a process. They're kind of doing it in different ways. So here's our Fibonacci solution, iteratively. I have trouble saying that word, but this is a simple solution for Fibonacci using loops. So if you remember the Fibonacci algorithm, it's basically the nth item in a Fibonacci sequence is basically the sum of the previous and the second most previous item. So that's what I've modeled here, where we have F, A, and B. We start with our base values for Fibonacci. 0, 0, and 1 are the first 3 items in Fibonacci. Basically, we compute the next value of Fibonacci by adding A plus B, and then we update our most recent and second most recent items to point to what we had before. I think there's a correct solution. Actually, let me code this out because I'm kind of staring at it. So let's code out Fibonacci. So I'm going to do fib.pi, fib.pi. See if I can actually copy this. Let's copy this from my slides. All right, hopefully that pastes correctly. Close enough. All right, this is Fibonacci iteratively. So let's do fib 5. I'm not sure what the answer there is. Let's look that up. So what is Fibonacci 5? Math is fun, sure. All right, so we have 0, 1, 2, 3, 4, 5. I think 5 should be 5. Let's go for 6 instead. So fib 6, I believe, should be 8, if I'm understanding this correctly. So let's print out the return value of fib 6. Well, let's see if this does this correctly. So I'm going to run Python fib 5. Fib is not defined. Oh, because I called it Fibonacci iterative. Always get to call functions that actually exist. All right, there we go. So we got 8 spit out from this iterative solution. Now, this works, but I would actually argue, despite this being a relatively simple algorithm, I can't just look at this and say, I know exactly what this is representing, right? I kind of got to go through, all right, we're computing something and then reassigning something here. It's not obvious, honestly, to me, what all is being accomplished here. I got to kind of stare at it for a while, and eventually I'll be able to figure out, okay, I understand we're combining some values and then updating some values. Something's happening here, sure. But this is a valid, correct solution for Fibonacci. But in this case, it's not always the most elegant. And we'll talk about the trade-offs again between recursion and iterative. Let's actually look at the recursive solution and compare it against the iterative solution. So if I go back to my slides, this is iteration. Not too bad. It's like 6 lines of code. This is the recursive solution. It's computing the same exact thing, but notice a couple things about it. One, we are calling the same function within itself. So this is recursion at play. We have Fibonacci recursive. We actually are calling back into Fibonacci recursive with some new values here. But in this case, we have this would be our base case. Let's actually copy this into our solution just to compare them. So expedite this process so don't make typos. Let's paste in Fibonacci recursive here. All right, and compare and contrast iterative versus recursive. So iterative uses loops. Let's use loops to solve this. And then this obviously uses, let's use recursion to solve this. Okay, so both will compute the same thing, just to prove that to you. I want to prove this to myself too, and just in case I've coded this up poorly. Recursive, both of these should print out 8, right? We saw that for the first one. Let's see what both of these spit out in unison. All right, so we get the correct answer for both. Again, not trying to pull any tricks here. Both are correct solutions for computing Fibonacci values. But here, I would argue this is a more elegant solution because less lines of code, and it's easier to understand because Fibonacci by definition is basically summing up the most recent and second most recent values. And that's kind of clear here, right? That's easier for me to see. Again, it might be subjective, but this is the definition of Fibonacci. It's one plus a previous. Here, we're doing something similar, like all this madness, not sure what that's doing. We have an n-1 here, so how far are we actually going? Again, both give us a solution, but this to me is a clearer solution. And that's one benefit of recursion potentially. It can make your algorithms or your code much easier to implement and to understand as readers of the code. I'm going to pause here and want to make sure we answer any questions between what the iterative solution and the recursive solution. Joseph?
On the recursive solution, if the sequence is supposed to go forward, how does that work when we're minusing 1 and then minusing 2? Isn't that going to make it go back?
Yes, that is one difference between the iterative solution and the recursive solution, actually. This actually computes forward. So we start with the lower numbers. Oops. We start with the lower numbers and then go kind of forward. Joseph is correct. This is actually kind of going backwards, where we start with like, hey, we want n equals 6. Well, then to get, recursive or fib 6, we actually need to get fib 5 and fib 4 first. So we're going to go, again, kind of go in reverse order, as Joseph pointed out. So that's saying, all right, we need fib 5 and fib 4. Well, what is fib 5 equal to? Like if we kind of do this in comments here, we need fib 6, right? Well, fib 6 is actually equal to fib 5 plus fib 4, right? That is the definition of how Fibonacci works. So then this actually breaks down to, if I can tab this out. Well, this is going to be, well, fib 5 is actually equal to fib 4 plus fib 3. That is what fib 5 is by definition. So that's going to be also plus, let me try tabbing that out too, plus fib 4 by definition is fib 3 plus fib 2, right? So you can kind of see how this is kind of breaking down into smaller and smaller pieces until we get to our base case. So our base case here, this is what actually stops us from continuing forever for this recursion. This base case says if our n value is less than 2, our fib value is going to be just the value of n. All right, so that's actually not going to make any more recursive calls. So as we keep going deeper and deeper, eventually we hit a point that says, all right, we're just returning a value, and that's going to kind of break this, not break this chain, but kind of go back downward. So maybe instead of just trying to whittle my way through words here, let's actually set a breakpoint here and use our call stack to see what's going on here. So what's the best way to do this? Yeah, let's just try this and see what happens. So I'm going to clear this. I'm going to run my code through the debugger. So I'm going to go to the run menu, start debugging, and we should eventually hit the breakpoint. All right, so we hit our breakpoint for Fibonacci recursive, right? Call stack, notice what's in our call stack right now. We have our kind of global context, and then we call Fibonacci recursive the first time. If we want to see our variables here, n equals 6 in this function right now. So if I continue, I'm going to hit, let's just hit play. So it's going to actually call into Fibonacci. It's going to do this first part right here, which is calling back into Fibonacci recursive. So let's hit play. So notice for this function call, I have n equals 5. But notice a new entry got added to the call stack. It's actually the same function because we're calling into the function. But notice a difference here. If I click on this, notice the n equals 6 for this context. For this function call, the value of n was 6. For this new function call, the value of n is 5, because that is what we called from within fib 6. So if I continue again, notice we get n equals 4. What's going on here? We're doing this part right here, where we said, all right, fib 6 equals fib 5 plus fib 4. Well, then we got into fib 4, and now we're doing this part right here. So we got to compute fib 4 now. So that's why n equals 4. As you can see, it's going to take a few function calls here. So I'm actually just going to kind of let this go for a little bit and keep them play. So notice that our call stack keeps getting more and more function calls. So I'm going to keep hitting play. All right, so I think we're building back down now. I think I missed that point that I wanted to get to. So apologies there. Let me stop this. I'm going to try that again. So again, we're doing fib 6. I added a new breakpoint where we get to the base case. So let's run this. Okay, so notice n equals 6 is our first fib call. That will in turn call into Fibonacci recursive with n equals 5. We get n equals 4, n equals 3, right? We're just kind of doing all these substeps because fib 4 equals fib 3 plus 2. But when we get to n equals 2, watch what happens. We no longer keep hitting this line. Sorry, n equals, oh, this is less than 2, my bad. All right, n equals 1 now. So we called, we're like 6 levels deep into our recursive call, but we got n equals 1. This is kind of like the tipping point where we're no longer gonna build up our stack. We're gonna start building down our stack. So we got to our base case, which is the end of our recursive line here. So return n. So now if I continue, this should be pulled off. This function's done. It's not waiting on someone else to return it something. So if I hit play, notice that we get n equals 0. Sorry, all right, so that got pulled off. We're back to n equals 1. I run this, we get n equals 2. So notice that this is shrinking now because we are actually returning values from this function call. Eventually we'll return from this function call. So again, I know it's kind of confusing, but it's basically just trying to get to this base case to get actual values that we can use. Because this is saying, well, I don't know the full definition right now. So it's, yes, it's going from top down saying, well, we need fib 5, so we need to compute that, versus the iterative approach computes fib 5, and we have that already. So, we go through this loop, we compute F0, 1, 2. This will compute F3, F4, F5. We kind of use those kind of in sequence. Sorry, that was a lot of me talking, so I want to hear you guys talk. What questions you guys have? Joseph, did that kind of make sense? And anyone else have any questions? Yilin, question.
Yes, so it's more about the Python language itself. So in the first iterative example, where you just declared f, a, and b just in one row.
Yeah.
Is that like something you can do only with integers, or you can do it with others variables?
You could do with others. Yeah, I kind of did some shortcut here. I could do this. This should be fine. Other languages like might not allow this syntax. I kind of did this I honestly did this to save some lines in my slides here because I can really fit it all. But yeah, normally, honestly, if I were coding, I would not do this all in one line. So I do f equals 0. I'd do a equals 0. Yeah, it means the same thing. You can do it with multiple data types also. It's just kind of a shorthand for doing it all in one line. I don't think it saves that much time, but yeah, it's the same. It means the same thing as this. But yeah, good for always good to clarify. Any other questions about any of the code that we've written here?
Does the call stack get bigger with the recursive function compared to the iterative one?
Yes. In fact, the iterative one does not add anything extra to the call stack because we're not calling any additional function here, aside from maybe range. It's like one and done. But if I put a breakpoint here and run this, we won't see anything more than Fibonacci iterative one time because we're not making additional function calls here. That is not what I wanted. Oh, because that should not be stuff. Whoops. Let's try that again. Let's put a breakpoint here. I probably could reload that. Okay, so I should be hitting reload. Okay, so we hit our breakpoint here. So we can keep track of our values. Again, this is kind of the nice part of debugging. We kind of see what's going inside of our application. We're not having to print so many times. But here, we're looking for n equals 6. That was what was input into our function. Currently, a equals 0, b equals 1, f equals 0. Let's actually see how these values change with our looping each time. So if I hit play, notice that the value of a, b, and f changed. Keep going. So we kind of see what's going on here. So we're building up Fibonacci values in sequence. A and B are your most recent ones. F is just kind of like a placeholder. So notice we get a equals 3, b equals 5. So we're building up that Fibonacci sequence. But our call stack here, notice nothing's being added to it. So we're not making successive calls to anything else. We're doing all the logic within a loop, and a loop does not add stuff to your call stack. So we do that. We get to our answer. So we got b equals 8. That should complete our range because that's what we're looping over. Yep, we get to our return statement. F should equal 8. That is our answer, and that's all we do. Okay, So that is a comparison of iteration versus Fibonacci. Again, this is a very, very, very simple example, a pretty simple algorithm, but just kind of highlighting differences. Again, iteration is actually faster, but the solution is not as kind of compact. So now that's a trade-off. Sometimes one might win over the other. Let's actually talk about the differences between the advantages of using recursion. So I'm going to say this up front. I rarely use recursion. I would say 95% of the time, the iterative solution is going to be easier to implement, and it's going to be more efficient. When we talk about like how quick it runs, again, that's my made up number 95% of the time, in my opinion. But there are some advantages to recursion. So one thing that we highlighted is that it generally can lead to reduced code. And then you might ask, like, what does it really matter if your code is like 2 lines versus 20 lines? Well, there are some considerations there. One of the main ones is the potential for bugs to creep into your code as it kind of is modified or even implemented initially. Think about it. There's 20 lines of code in my made up solution right now. That's 20 different spots or 20 different lines where a bug or a mistake can be made by a developer. So let's say, I code this up and I hand it off to Marcos. Marcos might, try to modify my solution. Let's say he needs to add on to it. Well, there's more lines of code, so there's more potential for him to maybe misunderstand something, accidentally, type something incorrectly. There's just a whole list of things that could go wrong with a larger code base. If there's only, 2 lines of code in like a recursive solution, for example, well, it's, there's still potential for bugs being added, but it's much more reduced because there's just fewer lines of code to screw up, if that makes sense. So reduced code can matter for development purposes. I'm not saying usually that should be your primary concern. I'd say most of the time you care about execution speed, and execution speed usually wins out in most of these battles. But again, code clarity has some value for development. So recursion can make code easier to understand and more easier to kind of work with. May lead to a more intuitive solution. Again, I think we kind of saw that with Fibonacci. In my opinion, the Fibonacci solution, the recursive solution for Fibonacci is clear to me. I totally understand what it's kind of trying to compute, versus the iterative solution takes me a bit to kind of understand what's going on. This third bullet point, it's rare, but it may reduce the time complexity of your algorithm. This is very specific to certain types of algorithms, but recursion could be a better answer for efficiency. Usually it's not. In the Fibonacci case, it is not a better solution. I don't know if you guys kind of noticed when I was kind of breaking this down. Notice that we're computing for Fib 5, we're computing Fib 3. Notice for Fib 4, we also need to compute Fib 3. We're actually doing redundant work with the recursive solution. So this makes it, you're doing more work, and it's just going to be kind of slower execution speed because you're kind of doing stuff over and over and over again. So again, this is not a more performant solution, but this is a more elegant, compact solution. Okay. Useful for, so there are certain like types of problems. So branching algorithms, divide and conquer, backtracking algorithms. These are certain classifications that algorithms may deal with. They may be easier to solve with recursion. Again, not necessarily better performant, but easier to solve using recursion. One example I could kind of come up with is searching a file system. So I actually kind of coded up a mock file system just to kind of talk about, hopefully we kind of understand the structure of working with files on our computer. So let me try to reflect this in a coding example. So I created a kind of a mock file system here. So in my file system, I have a bunch of folders. In this case, on the top level, I named it A, B, and C, and D, just to be uncreative. I also have a file called stuff.txt. There's nothing in there, it's just a file. But understand, just the basic file system has directories and files within them. But in my A folder, I have more directories and maybe a file here. If I look into my directories, I just created some random files. There's no data in here, but I have 1.txt, not text, 1.txt, 2.txt, but then my B folder also has some subdirectories. So again, it's just a hodgepodge of directory names. There's no logical naming for what I've done. I have potato stored in January. I have carrot stored in February. C also has some stuff based on states. I have donuts listed here somewhere. And then D has a little different structure. It has only one folder, but it has more levels within it. All right, so again, just a random file structure I created just to show this example. So the question is, what if we want to search our file system here and find something that may or may not exist in it? How can we solve this using loops or using recursion? Now, both are possible, but recursion for this particular type of problem is much simpler to implement. So I actually covered this up, so let's kind of just take a loop at it. So I have some, if you want to know some details here, I created some mock structures. So I have something called file, and all a file has is a name that I store in it. And I have something called a directory class that has a name. So like a folder has a name, but a folder can have some files within it, or it can have additional directories within it, right? So if I look at my file system for A is a directory that has a name. Its name is A. It has some files in it. In this case, monday.txt is a file. And then AA1, AA2, AA3 are directories within my directory right here. So I kind of just re-implemented a simple file system here with some structures. I create some data. So basically all this code that I've written here is to represent this file system that I've created here. So you don't need to worry too much about that. But the question is, how do I actually search through my file system? So here's my iterative solution. Now this is going to work, but it's not great, especially because we're doing the same thing over and over again at different levels. So first, I pass in a root directory. In this case, file system is my root directory. I'm going to search on that level to see if the file that I'm looking for, in this case, file name, exists here. So basically, I'm looping over all the files. In this case, there's only one file here called stuff.txt. Trying to find, do I find any file that matches what I'm looking for? If so, great. Return true, meaning I found the file. But if I don't find it on this level, well, then I need to search all the directories. So that's why I have my first for loop right here, where it's saying, all right, I'm in file system, give me all the directories. I have directory A, B, C, and D. That's what D1 is going to refer to. In each case, it's going to be a different directory. We need to search all the files within those directories. So in this case, if I go into directory A, well, now I got to search all the files here. In this case, there's only one called monday.txt. If I find my file, great, I'm done. But if I don't, well, I need to go into lower levels. So if you can notice, both figuratively and literally, we're going to lower levels in our directory and in our code, where we keep getting like these nested for loops here. So again, this is going to work. It's eventually going to search through all 4 levels I have, maybe 5 levels, but there are some problems here. One, repeated code. We're doing the same process over and over and over again at different levels. A second downside of this implementation is I'm assuming that I can only go 4 levels deep. What if I have 7 levels? Well, I need to add more code here, or maybe come up with a better solution is the likely answer here. So, this is going to work. It's going to look through every file and every subdirectory and repeat that process over and over using loops. This works, but it sucks in terms of coding it up. The recursive solution is much better. Here we have search data recursive. We pass in a directory name and the file we're looking for. And this is the idea of divide and conquer. We're doing the same thing over and over again. Recursion usually is better, easier to implement. So here, we're doing the same process where I say, all right, let's search all the files at this directory level. If we find our file, great, we're done. If we don't find our file, well, let's loop through all the directories on this level and then call back into our function. So here, this is our recursive call right here. Recursive call, right? We're calling search data recursive again, but instead of passing the original directory, which in this case would be file system, we're passing the current directory, in this case would be directory A for the first call. So here we're saying, hey, search data, search directory A for that same file name we're looking for. So we're going to come back here and now search within directory A. It's going to repeat that process. So again, same thing, same principle as we're doing here, but we're reusing the logic within the function recursively. So here, this is saying search all the directories for the file. If we find it ever, great, we can return true. If we don't find it, well, we continue our loop here. And then eventually when we get to the very end, if we never found it, we return false in both cases. Hopefully that's easy to digest. Again, high level, we're just searching through our files on our computer, looking for something. So my runner here, I want to find donuts or donut.txt, what I'm looking for. Well, if they're going to find it, just to prove it, I know it's not going to be too exciting, but we should be able to find it regardless of which implementation we want. So if I do Python runner.py. Notice I get true and true. So I did find it, like, to prove it's actually finding something. If I type in, something.txt, which does not exist, as in I know what files I created before. If I run this, they should not be found in either case. Yep, doesn't exist. Andrew, did you have a question?
Yeah, in this case, the iterative and recursive functions both have the same level of efficiency, right? Since they do the exact same thing.
That's a good question. I'm going to say not necessarily. Like, whoa, so not to get too much into this, but this is actually doing, I think, a BFS search versus this is doing, is that right? So this is depth first. Let's actually take a look at what's going on before I try to pretend I know what's going on. I'm going to add some print lines and let's see what gets printed out here. So where's my search? Sorry, I think they're both doing depth first because we go lower and lower. Let's add some print statements. So I'm going to do print. Print this out. Sorry, bear with me for a second. While I'm trying to add this in here, does anyone else have any questions about recursion or iteration?
Well, yeah, I was gonna ask, are we gonna go over like that first search? Because I remember on Boggle too, like that was pretty useful.
We're not going to specifically go over that today. I'm not sure if we cover that in our curriculum, but there, yeah, if you're curious, you could do, DFS versus BFS. That's depth first search, where you go all the way to the end of a line, trying to search for things, versus breadth first search. You kind of go level by level. Both are useful in certain cases. Usually breadth first search will give you the answer quicker, but that's not always true, if I'm correct in that. Let me do this here. Print. Root dir. Okay, sorry, I'm just trying to see what we can see the output as we're going here. Any other questions about recursion as we're doing this example? All right, let's see what directory levels we're going through. So if I clear this, it's going to be kind of hard to understand. Maybe D2 doesn't exist on line 8. It's D1. Okay, let's take a look at our output for our iterative solution. So how is this going searching through things? So it's going through directory A, searching all of its directories, then directory B. All right, so this is what we expect. We're going directory by directory and going there. Okay, so we made it all the way to directory D and searched all of directory D. That's because we're looking for something. Let's look for donuts instead. Donuts. See how this changes. It does. Okay, so we search directory A, then we search all of its directories. Then we search directory B, search all of those directories, and then, yeah, so this is still depth first. So it's going all the way to the end for A, but we find it in Illinois because that's where donuts exists. We have Illinois, we have donut.txt in folder C, subfolder Illinois. So that's the same process for what this is doing. So this goes through the same order, essentially. We search the parent and then the children of the parents. Yeah, so here, both of these are depth first. So sorry for any confusion there. Yeah, so they're not different approaches. They're just different solutions in terms of using recursion versus iteration. I don't know if that answered your question, Andrew. So let me come back to you.
It was honestly pretty useful just to see it printed like that too.
Yeah. So again, there's the idea of breadth first search, which we've not done here. If we're interested, just kind of give you a heads up. So there's a different type of data structure. We're using stacks here. There's a data structure called a queue, which allows you to implement breadth first search. So again, that's usually breadth first search can be useful to find kind of like the answer quicker in certain problems, but depth first search definitely has a place depending on what you're trying to find. But yeah, queues and stacks are similar, but also different. So we'll talk about data structures later this week. So we'll table that for now. All right, let's go back to our slides. Do you guys want a break? I feel like we probably need a break here. So let's actually take a quick break. We're almost done here, but let's take a. All right, so we talked before the break, we were talking about advantages of using recursion. Again, as I mentioned, 95% of the time, I think recursion is not worth it. Usually I just use, loops, iteration, and it's simple enough for most problems I'm solving. But again, recursion does have its place. As we saw, for example, searching a file system, recursion kind of is just made for searching trees, and it's better for using searching trees. So our solution for that was much more elegant and easier to implement. All right, any questions on the advantages of using recursion? Okay, but with advantages, usually there are disadvantages. So with recursion, disadvantages, usually, or not usually, it requires more memory for your application. So again, memory is one of those resources that we care about. Time is the other one. So usually you want our application to be really fast. So time efficiency really matters. Sometimes memory efficiency does matter also, as in how much memory does our algorithm require. In this case, it's a disadvantage to use recursion because all of those additional execution stacks that get added to your call stack, those take up some amount of memory. It's not free, it's just to add more and more items to your call stack. So that memory hit is definitely seen with more and more function calls that recursion has with it. Generally, recursive solutions involve more time complexity, as we saw with our Fibonacci example. I can pull that up again. All right, with Fibonacci, we're just doing some repeated work here. So that's actually, not a better efficient solution. So again, it usually, not always, it involves more time complexity to do recursive solutions. I'd say a lot of times it's gonna be the same complexity. Sometimes recursion adds more to it. Occasionally you could save time complexity, have a better time complexity using recursion, but that's not the typical case. On the last bullet point, can run into stack overflows, which will crash your application. So the background about this is basically your application is running on your operating system. Your OS is going to allocate some amount of memory that application can use. And if it needs more, it can request more potentially. But eventually it's going to hit its limit if you get into something that's called a stack overflow. So as I mentioned, every function call that you make within your application that gets added to the call stack, that takes up some amount of memory. So if you don't have a proper recursive design, you can get something that's called a stack overflow. So let's actually quickly see this. Andrew, you have a question?
Yeah, a while loop that doesn't end in an iterative solution, is it also called a stack overflow?
That is not a stack overflow. Good question, but that is a similar thing going on. So let's talk about both. Let's just go with bad code.py. So I'm going to do something called a stack overflow. And this is pretty simple to implement. So I'm just going to create a function. It's called overflow. Let's pass it some value n. Let's print out the value of n. And then let's return overflow n plus 1. All right, this is my function. It's basically going to call itself with the next value in the sequence. If I pass n equals 3, the next call would be n equals 4. So let's call our function here and see what happens. Overflow, going to pass it. Let's start with, let's see, let's go with, today is the 14th of February, so let's start with 14. All right, so let's just run this. So you probably know what's going to happen here, but if you don't know, we're basically going to call our function within itself. So this is recursion, but we're going to keep calling ourselves, right? We're going to call, overflow 15, overflow 16. That's never going to stop because we have not coded this up in a manner to tell it to stop. So if I run this, let's see what happens. I'm going to run Python bad code.py. All right, that was kind of quick. But let's see what happened here. So we are counting up. I'm not going to go all the way to the top, but notice that we're just printing out number by number. So that's what our function does. And then we make a successive call into overflow. So we keep going, but Python has some breakpoint, and that's what we got here. Notice we got maximum recursion depth exceeded while calling a Python object. So looks like we got to like maybe 1,000 calls because we start at 14. There's some limit that's built in here. So this is like a security check. Instead of crashing the application, it just says, let's just stop doing this because we know it's not going to end. So So yeah, again, that's what you get with the Stack Overflow. The reason we got this is because we did not implement a proper base case that tell us when to actually stop calling ourselves. We keep calling ourselves. So maybe we could do something like if n is greater than 200. Again, this is just a random example. Let's just return here. We don't have to return a value. So here we're saying we're done. Once we get to any value greater than 200, we're going to stop calling into ourselves. So here we should actually have an actual point, where we stop. So if I run bad code again, this should be good code. Notice it gets to some breaking point. So I have n equals 201. This gets checked and then returns so that we stop calling into ourselves. So that, again, that prevents a stack overflow. If we actually looked at our stack, we would see this, again, stack overflow. You probably can understand what's going on. We keep adding items to our stack. So if I run this through a debugger, let's see our call stack. So call stack, we have one item. Let's just continue. All right, we have more. So notice we're piling this up. We're never taking stuff off the stack. We're just keeping piling up more and more. This takes memory. Each one of these execution contexts reserves some memory within our application. Because if you notice, every execution context that I click on has a different value for n. So we need to store that somewhere in memory, right? We need to keep track of every variable for that execution context. In this case, we have one, but I can create more local variables here, like local var equals donuts. Let's say random var equals random dot random. Let's import that. I think you guys get the idea, so I won't belabor it at this point. But if I run this again and keep running it, so I have like 8 call stacks here. Every one of these have different values that are memorized or kept in memory. So my random var for each call is a different value. So that's still kept track of. I don't lose that, but that has a memory cost to it. So as we keep going, more and more memory is being used here. So I'm like a dozen calls right now. That's just gonna go to 1,000 eventually. Again, there's some limit baked in somewhere that says, all right, we're not gonna let you take up more memory here. So it just kind of aborts here. But if that safety check wasn't built in, your application would actually crash. Like if I built this application, handed it to someone, they tried to run it, it crashed the application. You get some like error report saying, hey, something wrong happened in this application. To Andrew's point, Andrew had a good question. What happens when you do something like, I'm going to use a for loop, but it's going to be the same principle. Let's write a for loop. So def pinned, and I'll try to do something similar. So for I, doing JavaScript syntax, or let's do a while loop actually. While print n, and then n equals n plus 1. All right, so if we have something like this, Andrew's question was, is this a stack overflow? Well, no, not quite. It's a good thought. It's similar. We're still going to get bad results. But what's going to happen here is something called, we're basically pinning our processor. It's going to keep doing this. It's not going to break necessarily. It's going to be locked in this loop forever. So it's going to still be computing stuff. It won't use extra memory because we're not storing memory between each loop call. So our call stack doesn't get exceeded, but we are going to get pinned here. So if I call pin with a value greater than 50, if I call it with 55, this is going to go on forever and ever. This is where you would have to use that Control C, or I think on Windows it's like Alt C to exit out of it. So I run Python bad code. That's not Python bad code. Notice it's going to go on forever. So this is an infinite loop, similar to Stack Overflow, but Stack Overflow will terminate because your computer is going to run out of memory at some point, and you're done. This will run until lunchtime. If you want to stay here for an half an hour, we could let this run. Obviously, we won't let that. If you get into infinite loops in Python, you can hit Control C, or in your terminal, hit Control C, and that should abort it. So I hit Control C, you know, we made 450,000 calls here, so that's a bunch of them. But again, this will run pretty much till infinity if I let it run. Obviously, I don't want to do that. But so again, both similar concepts. In one point, this actually is pinning our CPU, so we're stuck doing the same thing over and over again. We're never going to get out of it. This we're kind of making the same function calls over and over again, but this will actually crash your application. This will just lock your application in a kind of a death loop forever. Andrew, your question.
Just kind of an observation. It seems like even in the recursive case, like your compiler knows that it's recursive. Like it actually wrote in there recursive solution.
Yeah, so yeah, when it had that overflow, it said recursive call depth exceeded. So that's a good point. I actually haven't tried this out, but if we had like 1,000 different functions calling into one another, like our first example, I don't know if I have that example. Yeah, so if we had like 1,000 of these functions, I'm actually not sure if you'll hit that limit. So it might be particular recursion, but obviously I'm not going to create 1,000 functions here because that's not worth your time nor mine. But that's a good question. Actually, I don't know if that would trigger like a maximum call stack, but yeah, recursion is usually the case. You're going to hit it anyway. I usually don't get 1,000 function calls deep, but because it's possible without recursion. Okay, cool, good question. So again, that is one of the dangers of using recursion. You can run into Stack Overflow, but you can avoid it by having proper base cases, meaning you have a set case where you're going to abandon this. So in this case, we added a base case n equals greater than 200. Abort this operation. Any questions about Stack Overflows or I guess infinite loops? Again, similar concepts that you might run into, but that just means you need to kind of change your logic there. Ivan, question.
Is there any way to like once you hit an answer, like you got what you need? Is there any way for Python to just clear the call stack, or is that just like not possible at all?
I don't think that's possible. She's saying, hey, like let's say we're searching through a file system, we found our file. Do we actually need to go through like backwards through 20 levels, or can we just say we found it, chop off the entire call stack? The call stack, again, it's a stack, so we don't have access to everything in that stack. It's only the top. It's first in, first out. So we got to pull one plate at a time. We can't just toss a bunch of plates out of the pile of plates. But yeah, good question. I don't think it's possible. Again, maybe there's some weird library that can do it for you somehow. It doesn't sound like that's something that's possible in Python, from my knowledge. Well, all right. So again, there's many disadvantages of using recursion. As I said, most of the time, focus on an iterative solution. Don't just try to use recursion just because you know how to do it. Understand that recursion has some benefits, and only use recursion, I would say, when it seems beneficial. But again, recursion is not completely useless. I have had interview questions that specifically ask for recursion. So make sure you understand the principles, understand how to design solutions recursively. All right, so key takeaways, just know what a stack data structure is. That's what we went over kind of at the beginning here. Again, it's one of many data structures that developers or software developers can use. So again, lists and dictionaries, we've seen those a lot, but there's so many other data structures. There's stacks, there's queues, there's trees, there's hash maps. There's a whole list of them. Many are more, some are more, rare to see. There's also sets, which are useful for like unique data, but just understand there are more data structures out there that we don't necessarily use too often. Also know what the call stack is. Just kind of understand how your application is running and kind of organizing function calls. And they kind of build on top of each other. You can call functions within functions. Recursion is a case where a function calls itself as a function call. So that is how recursion works. So know how to use it and when to use it too. So again, usually for problems that you're doing the same process, kind of going to smaller and smaller locales. So again, file system search was one example. Another example you'll see tonight to talk about your challenges is binary search, where you kind of have a large search space and you're kind of narrowing it down, but doing the same algorithm over a smaller and smaller search space. Okay, so that is our recursion introduction, and also talk about the call stack. What questions do you guys have about recursion or the call stack or anything we covered today? Okay, guess we're probably gonna let that digest. You get more practice with recursion with the challenges, so I guess I could stop the recording.